An inverse square field. Okay, an inverse square field is defined to be as follows. We say the inverse square field is C u vector over the magnitude of vector r squared, which is also equal to C vector r over the magnitude of vector r cubed, where C is a scalar. Then the question is, why is this called an inverse square field? Well, for one, let's define what vector u is. So vector u is the unit vector of r. So to explain why this is called an inverse square field, if we take the magnitude of this vector, then we're going to get the magnitude of all these components, which then is this magnitude here, which then is C over magnitude of r squared. The magnitude of vector u is the unit vector 1. So there's a 1 here. And if you can see, if we call this magnitude of C like k, the constant of proportionality, then we can say that the magnitude of the inverse square field is directly proportional to the square of r, or the square of the distance from the origin. So it makes sense that it's called the inverse square field because its magnitude is inversely proportional to the square distance from the origin. Now let's prove that every inverse square field is conservative. Once again, I have it written up here, the definition of an inverse square field. I'm going to write it a little bit more explicitly. Let's say C. Now, what is vector r in terms of x, y, and z? Well, it's going to be x, y, z components make up vector r. And then if I take the magnitude of that vector to the power of 3, it gives me x squared plus y squared plus z squared to the 1/2, but then cubed, so to the 3/2 power. Now the goal is to prove that this is conservative. In other words, we want to show that this vector is del f for some scalar f. And in lesson 1, we came up with several ways to prove that some vector is conservative, or show that some vector is the gradient of some scalar. 1 was magic, 2 was through integration, and there were some other ways through theorems. But what we're going to say here is as long as I can have a function f, if I can come up with a function f magically through intuition or through computation, then I'm good. So all that I need for this proof is to come up with one. So let's call scalar f equal to negative c for some constant over the square root of x squared plus y squared plus z squared. Or written out as follows. So if this is correct, then del f, par f, par x, I want you to find that and find par f, par y, and par f, par z. And if you find each one of these, then they will hopefully be the components to this vector f above. So let's do it. So I have, bring down the 1/2, so I have c over 2, the negatives cancel, x squared plus y squared plus z squared to the negative 3/2 times the derivative of stuff, so times 2x. The 2's cancel out, and I have cx over x squared plus y squared plus z squared to the 3/2 power, which is indeed the x component to this vector f. Likewise, par f par y equals as follows, and par f par z equals as follows. And so from this, we can say that del f equals c over x squared plus y squared plus z squared to the 3/2 times vector x, y, z, which is exactly what we wanted to show. Q, E, D. Okay, we want to prove that the area of some region is equal to this. Da-da-da. Okay, let's start off with what we know. The area of some region would be the double integral over the region dA. That gives you the area of any region. And that would be equal to this. Par Q, par X minus par P, par Y dA. It would equal to that as long as the par Q, par X minus par P, par Y was equal to 1. And if it were equal to 1, then by Green's theorem, this integral here would equal the closed line integral. C is the boundary of region R, P dx plus Q dy. So let's take a look at this. Can you come up with a P and a Q that has the property here? Let's take a look. We can say that the area is equal to the closed line integral x dy. Now let's see, why is that true? Well, Q in this case would equal x, P in this case would equal 0, par Q par X equals 1, par P par Y equals 0. So the difference equals 1. So that says with Green's theorem, it's equal to, which is area. Good. Area, though, is also equal to this Now, why is that true? Well, in this case, P would be negative Y, Q would equal 0, par Q par X minus par P par Y is going to be 0 minus negative 1, which equals 1. So there it is. So that shows that this is equal to area, and it also shows that this is equal to area. So we can say now that 2 times the area is equal to this minus this from above. So therefore, area equals 1/2 the closed line integral x dy minus y dx. QED. Can you use that to prove that the area of a circle with radius a is equal to pi a squared? Everybody knows that the area of a circle is equal to pi r squared, but can you prove it using the thing we just established? If I come up with a parameterization for a circle, x is equal to a cosine t, y is equal to a sine t, and this is, of course, true for t between 0 and 2 pi. Dx, of course, would equal negative a sine t. Dy would equal a cosine t. Each of these has a dt in them. Then if I employ my formula above, I have 1/2 the line integral over c, the boundary, x dy minus y dx, which then equals 1/2 the integral from 0 to 2 pi a squared cosine squared t multiplying the x and the dy minus negative a squared sine squared t multiplying the y dx, all of this dt. And if we actually do this, it comes out to be a squared over 2 times the integral from 0 to 2 pi. Nice cosine squared plus sine squared equals 1. And we have already pulled out the a squared, so this integrand is just dt. So a squared over 2 times 2 pi a squared. Tell that to your friends at the next party that you can prove that the area of a circle is pi r squared.